5%. What I would see a lot of students do is I'd probably see them go 100 times 0.055, which is 550, and then they'd go 100 plus 550 is 105.50. Okay, and they do that. And then for the next step, they do the same thing. Like they times it by 5.055 again, and then add it to the same total, and then they get the new number. But that makes two steps, right? Like that's very clearly a two-step situation. Whereas if you just used an exponential equation, you wouldn't have to do two steps. So instead, what you can see here, like instead of multiplying by 0.055 and then adding 550, if you just multiply by 1.055, it just does it automatically. Like it adds the one as well. Because what you're technically doing then, just to be really clear about it, is like I'm going 100 times 1 plus 0.055, and what you end up doing is you're expanding this. So it's like 100 plus 100 times 0.055, which is exactly what I did down here. Like it's exactly the same as this, just in one step. Okay, that's why it works. Now, if you were losing money, like if we had a situation where you bought a new car and you were looking at the depreciation rate, like how much it decreases by each year, that's usually how we do it. It's like a new car depreciates at a rate of 7% per year or something like that. What would change? Yeah, that's exactly it. All that would change if it was depreciation instead is instead of plus, it would be minus. So instead, if like it's better to think of something like if something's shrinking at a rate of 7%, that means that next year it's going to be 93% of its current value, right? Does that make sense? Because it was at 100, we're going down by 7%. Ooh, that's weird. Oh, shut it down. This like just has, look, student number 1, Callie. That's my student that I stalk. Okay, it's weird. No, it's me. That's no, that's my name. That is not math related. I don't know what's going on with that. Okay. So it's minus instead if it's depreciating. If it's growing, it's the same thing. Like if something's going to be 10% more, you should be thinking about it was 100%, it's 10% more, now it's going to be 110%. That's how I always think of it. It kind of makes it a little more clear. Conrad? Oh, not anymore. Oh, okay, actually, this is out. Okay. Here, we're just going to talk about what an exponential function is. So if a is a positive real number other than 1, so as long as a is not 1, if a is 1, what happens with our exponential function? Well, we can still have 1 to the power of x. What would that do if I graphed it? It would just be a line. It would be a horizontal line. So it's not really, I mean, it's still a function, I guess, but it would just be like a horizontal linear function. So it would not be, it wouldn't be exponential in the end. It would look exponential, like 1 to the power of x looks exponential, but if you actually graphed it, the graph would not take the shape of an exponential function. So you just saw just now, if whether or not you take Math 30, you just got to see what exponential functions look like. So they either look like they're going up really steeply, like that, or they're going down really steeply. It's one or the other, right? It's either increasing or decreasing. That's why when people talk about like, I'm doing exponents in my grade 9s right now. And, it's like when people are saying just on TV shows or whatever, they're like, it's growing exponentially. That usually means it's growing really, really fast. Okay, that's just the way we say that. It doesn't necessarily, when people say that, usually it doesn't mean actually exponentially. But it just means that it's growing really quickly. And you can see that with the graph, right? Like it starts off, it's like, kind of like, oh, it's not really growing very fast, just going up a little bit. And then all of a sudden, it's like steep, like right upwards. And you're growing super, super fast. So that's what an exponential graph looks like. That's what we're talking about here. So if you're given a function like this one, okay, it asks you to do it using your calculator. So maybe just do that right now. Just on your calculator, graph 2 times, and you can tell it's with your calculator, okay? Like sometimes you need to use a little bit of common sense here. It gives you windows. If it's giving you windows, it clearly wants you to use a calculator. So if we graph this thing, using these windows. And it's good practice just to get into the habit of, graphing and changing your windows and being really comfortable with that stuff. Okay, 2 times 3 to the power of x minus 4. I would say the big thing here, not to do, and I see very bright students do this pretty often, is I'll get pretty bright kids who do this, and they're like, okay, 2 times 3 to the power of x minus 4. Okay, well that's the same as 6 to the power of x minus 4, and they'll change it to that. Okay, that is not true. Okay, so 2 times 3 to the power of x is not the same as 6x. This is false. Okay, do not do that. Why are they not the same? Might be right out. Anyone know why they're not the same? Well, it will make it different for sure. The reason that you're not allowed to do this really, I guess we could talk about reasons for a while, but FedMath, like order of operations, states that you have to do your exponents before you do your multiplication, right? There is an exponent here. 3 to the power of x, that's an exponent. You can't do the multiplication with it because you haven't done the exponent. And you're not going to be able to do the exponent because the exponent is an unknown. It's x. It's a variable. So we're just going to have to leave it. Like this is already simplified is what I'm trying to get at. You cannot simplify this more. Now, if we look at this, okay, what is the y-intercept of this graph? -2. Okay, so it's down here. It's -2. Okay, and is my graph increasing or decreasing? Increasing? Now, how would I know, just looking at this graph, or looking at the equation for the graph rather, not looking at the graph itself, how would I know that it was going to increase without using my calculator? No, it's not. Well, yes, actually, I guess that's good. It's not a negative exponent. If it was a negative exponent, that would make it decreasing. The other thing that is actually the same as it being a negative exponent is if the number is a fraction. Okay, so for instance, if you had it's exact same equation, but it was 2 times 1/3 to the power of x minus 4, that's equal to 2 times 3 to the negative x minus 4. Those are both the same. Okay, those are just the same thing written 2 different ways. Because remember we talked about how negative exponents just move something down to the denominator. So either of these equations, these would be decreasing. Decreasing. Okay, whereas if the number is like a whole positive number greater than 1, or actually it can be a decimal greater than 1 too, if it's any number greater than 1, the exponent, then you will have an increasing graph. So our graph is increasing, so it looks, something like that, just going through -2, and evens out there. Now, does anyone have an idea of how I can get the -2 without having to use a calculator? Make x 0. Yeah, that would do it. So if you make x 0, I know 3 to the power, anything to the power of 0 is? No. 1. Okay. I just did it with my grade 9s too. Actually, I didn't. The student teacher did, but I watched him do it. He explained it to them. Okay, so anything to the power of 0 is 1. Okay, so 3 to the power of 0 is 1. So we have 2 minus 4, which is -2. This is also there is like a transformation going on and everything, but that's probably the easiest way to do it is to just, and I'm not going to be asking you to do tons with these graphs, to be honest. I don't even know. Like, you probably won't even really have to graph them, but you should be pretty familiar with them. Like, if you see a graph in this shape, knowing it's an exponential function. Okay, and knowing, really, I'd like you to just be able to tell the difference looking at an equation if it's going to increase or decrease. Okay, so I'm not looking for time. Okay, we're looking at it pretty simply. Now, these are the exponent laws. Okay, you've seen them before in grade 9, as well as after that, probably. I'd say the top 3 are like more important. It's really important to note that, just to remind you guys, that this is not a law. This is not a law. I can't be more clear about that. This is like, I'm writing something that is not a law. You cannot say this. Okay, this down there in blue is not something you can do. You cannot have two things adding in brackets to the power of x and then just make them both go to the power of x and have them add separately. You cannot do that. It works with multiplication. It does not work with addition or subtraction. You would have to, if you actually wanted to do that, what would you have to do? You'd have to expand it however many times. So if you had a plus b to the power of 2, you'd have to go a plus b times a plus b, and then do all your arrows and all that nonsense. Okay, does everyone know all these rules? Like if you multiply two powers at the same base, you add the exponents. If you divide, you subtract. If you have power to a power, you multiply. These look familiar to people? I hope. Sort of. A little. People are with me. I'm not sure. I'm not really sure if you're with me or you'll like keep going on it anyway. What were you writing?
Some, because I didn't know them. Well,
But they're in your notes.
Oh, yeah. Okay, never mind.
Okay, I'm not gonna do this. Yeah, I want people to do a little bit of practice at this right now. We're not gonna do very much textbook stuff, but we are right now. So